In this lecture, we will discuss about the transfer function. What is a transfer function? And we will try to understand the basic concept of transfer function in control systems. What is the use of transfer function in control system? So this lecture will cover the introduction to the transfer function. And we will also see that why we use Laplace in control systems, and then what is the procedure to determine the transfer function, and then we will also have a look on the methods which are used to obtain the transfer function of a given system. So to start with, what is a transfer function? So transfer function is basically a mathematical relationship between the input and output of a system. We know that any system has some excitation, right? If it has some input here, so definitely the system will have some output if it is working properly, right? And if there is an input and there is an output, corresponding output of that input, or you can say there is some excitation to the input, and with respect to that excitation, the system gives certain response. So the mathematical relationship between the response of the system with the excitation to the system, or you can say the output of the system to the input to the system. So this mathematical relationship between these two is the transfer function. However, there is a special condition for this, and the condition is that the system shall be or must be initially relaxed. So by definition, we can say that transfer function is actually the ratio of the Laplace of output of the system to the Laplace of the input to the system, and assuming that the system is initially relaxed. Now, initially relaxed means the initial conditions of the system should be zero, right? So this is what we assume, and this directly or directly means that the system is initially relaxed, and then in this condition or under this condition, the ratio that we determine by taking Laplace of output and Laplace of input, that gives us transfer function, right? So as you can see here, this is a block, simple block, and it has an input and output. So this block gives the transfer function of the system, right? So if the input is represented, so if we represent, so there is certain representation notations. However, there is no thumb rule for this. We can take any notation. However, if we take notations on our own, then we need to specify their meanings. Their nomenclature has to be used, right? So in general, we will find in literature that the input to the system is represented by RS, and output to the of the system is represented by CS, and then the transfer function is given by GS, which is equal to Laplace of output, that is CS in this case, and Laplace of input, that is RS in this case. The ratio of these two gives us the transfer function. So the output, the response of the system, depends upon the transfer function and RS. So this is actually the gain of the system, right? So transfer function also gives us the gain of the system, right? Now, uh, there is a possibility that when we find out the transfer function of any system, the output and input may be different or maybe of different types, right? For example, there is an electric motor, right? In electric motor, the input is electrical quantity and the output is mechanical quantity. However, in generator, the input is mechanical and output is electrical, right? However, in this transformer also, we can see that the input and output both are electrical. So it is possible that the system which we are dealing with and we are trying to find out the transfer function, that system may have different input and output, right? Different types of input and output. There may be possibility that the input or output are same as in this case of transformer, right? So this is one example actually. So if Rs is the input, Cs is the output, Gs gives us the transfer function where Rs is the Laplace transform of Rt, where Rt is actually the time domain function of input. So this is the input and this Ct is the time domain function of output signal respectively. So this is how we represent the transfer function of any system. It is very easy and simple, right? Okay. So now to find out the transfer function of the system, we need to apply Laplace transform on the given, equations of the system, and then we need to find out. Okay, so Laplace is very important tool that plays an important role in the control theory, and some of its, points which make it important for the control systems are like the Laplace transform is useful for the study of transient responses, or you can say time responses of linear time invariant systems, right? So by using Laplace transform, it becomes convenient for us to analyze the transient characteristics of the given system, right? Like we can analyze the rise time, peak time, settling time, overshoot. So we can analyze these transient characteristics of or dynamic characteristics of the given system, linear time invariant system, right? So Laplace is also used to describe the behavior of a system, right? No, we can derive the transfer function using Laplace. Okay, how that will come in the next slide. Then it is easy to obtain the frequency response of the given system through transfer function. Now, once we derive the transfer function of the given system, so it becomes convenient for an engineer to study the frequency response or to determine the frequency response of the given system through transfer function, right? So these are the points which make Laplace an important tool for the control systems. Now, how can we determine the transfer function? As it is been mentioned in the previous slides that transfer function gives us a mathematical relationship between the output and input of a system, response and excitation of a system. Okay, so by definition, transfer function is the ratio of the Laplace of output to the Laplace of input with initial conditions 0, right? So that means we need to apply Laplace transform here, right? So Laplace of output. So we can apply Laplace where when we have some equations. Which type of equations? Time domain equations, right? So the first thing that we do to get the transfer function of any given linear time invariant system is we derive its equations. We do this is what we call as mathematical, we derive the mathematical equations, right? So now then what do we do? Because as per the definition of transfer function, it is the ratio of Laplace of output to the Laplace of input. So once you get the mathematical equations of the system, so then you apply Laplace transform on the given equations. And when you apply Laplace transform on the given equations, all the initial values, initial conditions that come after applying Laplace transform, so all these initial conditions are kept 0. So we put them 0 so that we get an equation without the initial conditions, right? And thereafter, so once we have applied Laplace transform and we have put all the initial conditions as 0, then we specify the output and input. Now we rearrange the equations. Okay, so what does it mean? It means that we rearrange the Laplace transformed equation in terms of output and input. Okay, so we separate the input parameters, we separate the output parameters, rearrange the equation so that it becomes easy for us to take the ratio, right? Then the last step is that we take a ratio of Laplace of output to the Laplace of input, and that would give us the required transfer function. So now let us understand this with an example. And so here is an example. This is an electrical system wherein we have a resistant and inductance. They are connected to one another in series across a voltage source V. And there is a current that is flowing in this circuit, in this path. Now, if we have to find out the transfer function of this particular type of system, so we need to first of all determine the equation of this particular system. So the first step is derive the mathematical equations of the given system, right? So let us find out its mathematical equations. So we can apply KVL here. So apply KVL in the given circuit, right? So the KVL equation will give us V. Suppose this is VII for input, right? So this is VIT and minus IR minus LDI by dt is equal to 0. So VIT is equal to IR plus IL di by dt, right? This is, for example, equation number 1. Similarly, the output equation of this is V naught T, and this is equal to L di by dt, right? So this is second equation. Now the second step is step 2. Step 2 is apply Laplace transform on the equation 1 and 2, right? So if we apply Laplace transform of these equations, VIT is equal to Laplace of IR plus Laplace of LDI by dt. Similarly, Laplace of V naught T is equal to Laplace of LDI by dt, right? So the Laplace transform will give us VIS is equal to IS into R, right? Plus, so this is a derivative term. So the derivative term will have S and the variable is I. So it is ISIS into L. This is the constant value, right? L is the constant value. See, this is, for example, equation number 3. And similarly, we can determine the Laplace transform of this particular equation, output equation, which is V naught S is equal to L S I S, right? So this is for equation number 4, right? Now, in this equation, we can see that uh, this is a simple equation, right? So we don't have to rearrange this equation to find out the inputs and outputs, right? So this is the simple equation. So step 3 is, here we know that this is the input and this is the output, right? So now we can simply come to last step and we can say that this is step 3. Take the ratio. So take the ratio, right? So the ratio is V naught S by VIS. We have to take the ratio of input and output. Means we have to take the ratio of, as per the definition of transfer function, which is ratio of Laplace of output to the Laplace of input, right? So V naught S is equal to SLIS and VIS is equal to RIS plus SLIS, right? Okay, so now if we have to further solve this, so we can simply take the common term here and cancel it out. We can see that is a common term here, which can be cancelled out, right? And as you can see here, this is the Laplace of output to the Laplace of input. And while taking the Laplace transform, we have already assumed the initial conditions 0 here, right? So GS is equal to V naught S divided by VIS is equal to SL R plus SL, right? So this is the transfer function of the given circuit, this circuit, right? So I have cancelled out this IS. You can see this IS is common here, so it will be cancelled out from numerator and denominator, right? Okay, so this is one kind of example. Similarly, we can have mechanical systems, we can have electromechanical systems, we can have different types of systems. So what we have to do is we simply have to formulate the mathematical equations of that particular system, and then we have to apply the Laplace transform. Okay, so it is that simple. Similarly, we have one such system here also, so we can simply apply the same method, same approach as we did in the last example. So step one is formulate the equations. So equation may be static and dynamic, right? So we have to find out the dynamical equations given electrical system. So what are the equations? It is EI minus IR minus LdI by dt minus 1 by C integration I dt is equal to 0. So if you see here in this particular mesh, the KVL equation is, so this is the KVL equation, right? Okay, so this is, for example, equation number 1, right? Similarly, we can say the output equation. The output equation is, it is E naught is equal to 1 by C integration into I dt. So this is equation number 2nd. Now step 2 is apply the Laplace transform on equation 1 and 2, right? So equation 1 will give us EIS and minus ISR minus SLIS minus 1 upon S. Integral term will give you 1 upon S, right? And C and IS is equal to 0. So you can see if we rearrange this one, so we get EIS is equal to R minus R plus SL plus 1 upon SC, and IS is a common term here, right? Similarly, the Laplace of out equation 2 will give us E naught S is equal to 1 upon SC into IS. So this is, for example, equation number 3. This is, for example, equation number 4, right? So we can simply come to last step, because there is nothing to rearrange in these two equations, right? These two equations are quite simple. Okay, so take the ratio, right? So it is E naught S divided by EIS is equal to 1 upon SC divided by R plus SL plus 1 upon SC, right? So we can simplify this equation. So it is SRC plus S square LC plus 1 by SC divided by SC. So this is here cancelled out. So we will get GS is equal to 1 upon S square LC plus SRC plus 1. So this is the transfer function of the given circuit which is shown in this slide. So it is quite simple. Okay, so we simply have to formulate the equation, take Laplace, rearrange, and then take ratio. Now, see, the transfer function of any system can be obtained by a simple rule, and that rule is derive the mathematical modeling of the system, equations of the system, take Laplace, and that, right? However, there are some another methods also which are generally used to determine the overall transfer function of the given system. In this, the first method is the block diagram method. So at times it becomes very inconvenient or difficult to derive the mathematical equation of the complex control system. If the control system has, the complex equations, mathematical equations, so it becomes very difficult to, derive such equations and then take their Laplace. Okay, so now what we do is, instead of writing the mathematical equation, we represent the transfer function of every element in control system, and we represent it with a block. So every element will have a block, right? And these blocks may be connected in cascade, in series, for sorry, in parallel, or in any other complicated manner, right? Now, block diagram reduction techniques are applied to obtain the desired. Now, what we do is, first of all, we represent the element of any control system with a block. Then we apply block diagram reduction techniques, and then we get the desired transfer function, right? Okay, in this way, we have another method which is signal flow graph, SFG, right? So what is this? This is also a pictorial representation of a system, right? And this is a modified version of block diagram representation, right? So that means we can represent a system with its dynamical equations. We can represent a system through block diagram, and we can also represent a system through signal flow graph, right? So signal flow graph is a kind of modified version of the block diagram representation, right? This is a pictorial representation. And signal flow graph, what they indicate, the how the signal is flowing in a particular control system, right? And signal flow graph representation is bit easier than block diagram representation. That means if we have to solve a block diagram of a given system, and we have to solve the signal flow graph of the same system, so signal flow graph will be solved conveniently as compared to block diagram, right? So in this lecture, we have understood about the transfer function. What is a transfer function, why it is used, what is the role of Laplace transform, and we have seen how we can derive the transfer function of the given system. Transfer functions have some, limitations basically, and the limitation is that, limitation of transfer function. Now, what is the limitation of transfer function? As you can see here, the system needs to be initially relaxed, right? So the to obtain the transfer function of any given LTI system, we have to assume the initial conditions equal to 0. Okay, so this is a limitation basically. So but see, we cannot do anything with this, because also the second limitation is the transfer function does not give any indication what internally is going on with the system. It simply gives a relationship between input and output of the system. It doesn't give any insight of the internal dynamics of the system. Okay, internal dynamics are not, cannot be, considered with transfer functions. So these are the limitations, right? So in this lecture, we have discussed all this, and so now it is here ended. So thank you so much.